Sputnik was the very first artificial Earth satellite launched by the Soviet Union during the beginnings of the Cold War and began the space race. But now we have come a long way with hundreds of satellites orbiting the Earth for surveillance, weather monitoring, navigation, your internet connection, etc. With all of these satellites above us, have you ever wondered why don't they just fall on us or fly away straight into deep space? The answer is in this session. To understand this better, we will consider a much simpler version of this question. When an object is moving in a circular path at a constant speed, we can say that the object is in uniform circular motion, just like a satellite or the Earth around the Sun. Let us take the constant speed of this object, and the radius that it is moving through is capital R with the center C. Let's assume that this object, the Earth for example, is moving at a constant speed, and the radius of its circular path is capital R centered around C. As we can observe, the direction of the velocity of this object keeps changing. Thus, it is undergoing acceleration even though the speed remains constant. To understand the magnitude and direction of this acceleration, let us consider two position vectors r and r dash. When the object is at P and P dash for a given time interval delta t, that is, the object is moving from point P to point P dash in that time interval. By the triangle of vector addition, we can find the change in velocity, which we also call delta v. Since the path is circular, the velocity vectors v and v dash are perpendicular to the position vectors r and r dash. Similarly, the delta v, that is change in velocity, is perpendicular to the change in the position vector delta r. With this in mind, if we place delta v on the line that bisects the angle between r and r dash, we see that it is directed towards the center of the circle. So as you can see here, the velocity is being directed towards the center of the circle. Since we now know the direction of change in velocity vector delta v, we can find the direction of the average acceleration a during this time. We know that the average acceleration is given by a is equal to delta v upon delta t. Therefore, the acceleration is along the change in velocity vector delta v, and thus the average acceleration is also being directed towards the center of the circle. This is true for varying time intervals. So you can take any 2 points on the circle corresponding to a time interval delta t, and as long as the speed of the object remains constant, the acceleration will also remain constant. This will hold true even when delta t tends to 0. And at that time, the average acceleration becomes instantaneous acceleration, which is still directed to the center of the circular path. Since the change in the velocity vector delta v tending to 0 is still perpendicular to the velocity vector v. Thus, the acceleration of the object in uniform circular motion is always directed towards the center of the circle. Now, the magnitude of acceleration is by definition given as the change in velocity to change in time for the time interval tending to 0. We know that the angle between the position vectors r and r dash is delta theta, the change in angle. And since the velocity vectors v and v dash are perpendicular to these position vectors, the angle between v and v dash is also delta theta. Therefore, the ratio of the base length to the side length for one of the triangles is equal to that of the other triangle. And this is given by delta v by v is equal to delta r by r. So this gives us that the modulus of delta v is equal to v times modulus of delta r by capital R. Equating the equation 2 to equation 1, we get a new relationship. If the time interval delta t is very small, then the change in the angle delta theta also becomes very small, which makes the arc length pp dash approximately equal to delta r. Since the arc length can be shown as the product of the velocity and time, we get a new relationship, that is, the limit delta t is equal to 0, delta r by delta t is equal to v. Therefore, we can say that acceleration, or in this case centripetal acceleration, is equal to v square by capital R, where r is the radius of the circular path. Thus here, by equating the previous two equations, we get the magnitude of acceleration. Now this acceleration, which I mentioned earlier, is called centripetal acceleration. Why? Because it is always directed towards the center of the circle. Centripetal simply means center seeking. The angular velocity omega is given as the time rate of change of the angular displacement, that is delta theta by delta t. Now, if the distance traveled by the object during the time delta t is delta s, that is pp dash is delta s, then v is equal to delta s by delta t. But we know that delta s is equal to capital R multiplied by delta theta from earlier. So equating those terms, we get v is equal to capital R delta theta by delta t. And equating those equations, we get v is equal to capital R multiplied by omega. Now, equating equation 7 with equation 5, we get an alternative equation for centripetal acceleration given as AC is equal to omega square R. Now, according to Newton's second law of motion, we know that force is equal to mass times acceleration. So, equating equation 5 with equation 8, we get two distinct formulae for centripetal force, Fc, which are given as follows. Now, same as the acceleration and velocity vectors, the centripetal force is also directed towards the center of the circle. Now, we come back to our original question. When a satellite is traveling in orbit, all it wants to do is travel in a straight line due to the inertia as defined by Newton's first law. But the centripetal force that we have discussed pulls on the satellite maintaining an orbit around the Earth. Now remember, centripetal force is not some special kind of force. It is always being provided by some other known force. In this case, the centripetal force which is preventing the satellite from being thrown away is the gravitational force. Thus, the inertia of the satellite prevents it from falling towards the Earth, while the centripetal force in this case, the gravitational pull, prevents it from flying off. And that is why it is able to maintain a stable orbit, neither falling towards the Earth nor flying off into space. So let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.